So my presentation is about a software approach to PIC design. And so let's get started. So if you think of PIC design from a very abstract, high-level point of view, so you have an idea, you then do a design, you then go to manufacture your chip, you then have the chip, and then you do measurements, packaging, and you have your product. So now there's usually a certain lead time in making this. So there's a certain time you need for the design of the chip, can be anything between 2 and 4 months. There's the fabrication, which can be anything between 2 and 9 months. And then there's usually a cycle. There's a number of iterations required. Now, if you look at the electronic IC design, when there's typically the first time right approach, so you don't have these cycles, but given the current ecosystem in photonics, and it's not yet very mature, you usually have these cycles. So the question here is, can we control this time to either a research paper, a demonstrator, time to market, or market share? And so let's have a look at what things we have control over and which don't. So the fabrication process is typically you send your GDS to the foundry and you will have to wait until it returns. And so you don't have a lot of control over that. In terms of designing and in terms of number of iterations, you can have control, and the way to reduce these is by using Tarov design automation. And that's what our company is about, and it's also our vision in the future that PIC designers can have the same first time right experience as electronic designers. Just a small example of what I mean with automation. So imagine that you've made a certain demonstrator chip, and 1 year later you have measured the device, you need to change X, and so your manager says, no problem, redesign. But then you may ask yourself, it's 1 year later, how did I make this 1 year ago? How did I run the simulations? Or which design rules were important for this specific foundry? It might be a while ago and you might not remember everything very well. Now, if you have a very clear documented flow, which is automated, and you have reproducible steps towards building this chip, you can actually do a significant effort in reducing the effort to make the chip. So in this presentation, I'll talk about two things. First, what are the typical PIC design activities? And then how can you manage this full design cycle? So the first part, what I will touch on only briefly, because I want to focus most of the presentation on the how. Okay, so what design activities are there? And I'm taking an example of a chip that Luceda has been designing. It was a demonstrator for space RF applications together with Astron in the research project. And this was done in late technology. And so if you look at the building blocks that you need, there's multiple libraries involved in this process. And so there's the Foundry PDK, which provides you with, let's say, the fiber couplers, the bond pads, some modulators. There is an assembly design kit, which tells you the rules on how to place your fiber couplers, the bond pads, and so forth. There might be third-party IP, which you insource from a design house. And then there's your own internal library, let's say, with a variety of cells and maybe routing functionality that you write yourself specific for this design. And now for all of these libraries, there are certain activities that you need to do. These can range, let's say if you talk about a PDK, you're more in the realm of doing component layouting and optimization, making 3D geometries to send them to physical simulation tools. And then when you move up the hierarchy, let's say, you're moving more towards doing circuit modeling, building compact models, running circuit simulations and layouts. And then once you have your chip measured, you can then start improving on your designs. And now all of these activities, they are supported by IPKISS. So IPKISS provides, that's our software product, provides for each of these activities a solution. Now, as said, I want to focus most on the how. So let's look at how we can improve on this cycle. And to do that, we first check on the requirements for doing PIC design, but again, from a high-level perspective. So definitely something you want is to have fast iterations. And also you want to be able to deal with complexity. And with complexity, I mean in the like when chips become larger and larger, it becomes important to be able to abstract your complexity to work more efficiently. Dealing with uncertainty can be from a technological point of view. For example, the foundry variability is something you don't control, but also project planning. Those type of uncertainties are always there when you build such a chip. Scale, you want to deal with scale, both in terms of your design team and in terms of your chips, and you want to have a predictable flow. And interestingly, software development has very similar requirements and challenges. So the ones which I listed here, they're also there when you want to build a product. So the question here now is, can we reuse these techniques from software development when you do PIC design? And to answer that question, I'll talk about 4 aspects in software development and how they can translate to PIC design. So let's start with the first one, and that's doing design capture with code. So you have a certain idea for a chip, and the idea is to bring that into a piece of code. So you capture your design intent in a programming language. And in this case, this is Python. Python is a very popular language in data science, but also in photonics. And then you have a photonics domain-specific language on top, and that's what IPKISS will help you with. And so we encode all the information that you need to do photonics within a layer on top of Python. And from IPKISS, you then generate various outputs. It can be generating a GDS file for manufacturing, running circuit simulations and doing circuit analysis, running exporting 3D geometries so that you can import them in dedicated EM simulation tools, such as Lumerical or CST Studio Suite. Or you can bring all these blocks which you built in Python, you can bring them into an EDA tool. So this is I'll-edit by Mentor Graphics, where we have actually designed something in Python and then export it to this EDA tool so that you can reuse them in your favorite EDA tool. Okay, what does code give you as well? Code helps you building layers of abstractions. So one obvious layer of abstraction are PDKs. So this is a list of the PDKs that we support today. And you can see a PDK also, if you think of code, you can see it as a module, which you use as a layer of abstraction. And so you don't have to care about all the information and the details from the foundry. They are abstracted away for you in the devices that you use. Another layer of abstraction can be your own libraries. It can be a 100 gigabit transceiver library, which you built. This is now a module in a piece of code, which you can then reuse across multiple projects. Or, for example, you can build more complicated macros. Macros are functions written in a piece of Python code, which you feed in a certain input, and then out comes a full photonic device, including layout and models. So this is an example of an AWG, where you start from the free spectral range and the center wavelength and some other specifications, and out will come a fully manufacturable AWG. And code really helps you in abstracting away all the details so that you can focus as a designer on what really matters, and it's building your circuits and your chips. The second aspect is version control. So when I did my PhD and I was very ignorant about writing software or writing codes, I used to organize my files like this. But in software development, it's a very known practice to use version control. And that in version control, you just keep one file, one version of the file, but it's stored throughout history. And so you can have a design history, which you can always access at any moment. You can see who has been working on the file and have been making changes. And it's easy to spot where changes have happened in the past. And one of these very popular repository systems is called Git. And Git is a version control system. The idea is that you have your PIC design, it's stored into this repository, and the master is the so-called stable branch. And from there, you can have multiple branches where you try out multiple design variations. And the advantage when your design variation is done, you want to bring everything back to the master. And at that point, you have the opportunity to share your knowledge with your team, to do QA, to review code. So this is a very scalable way to work together with multiple people. In addition, because this is written in code, Git is very good at automatically merging file conflicts. So even if with multiple people you work in the same files and in the same project, Git helps you to automatically merge any possible conflicts and brings all these files together. The third aspect already touched upon previously is automation in PIC design. So taking the same chip I showed in the beginning, there's a lot of automation that happened here when we built this design. So first of all, there's the building of compact models, which we automated. So for example, to make this direction copper, there's different macros that were written. So there's a Maxender macro which we built, so you can actually make a multiplexer very easily based on high-level specs or the ADBGs. There's automated routing, which we implemented, and there's a lot of other things you can do fully automatically. And once you have this, if like 1 year later you need to do a small variation, say you want to change the free spectral range of this Maxender lattice, you just change it, rerun throughout the whole flow, and the chip will just adapt. And now when you bring everything together, and this is where software development has done a lot of progress in recent days, and that is when you use continuous integration and continuous delivery. So the concept is as follows. You have a repository where your PIC design lives, and each of these items is a change set which contains a certain variation of your chip. And so now as a user, what you can do is you can write a set of actions that you want to be performed anytime you make a variation. It can be anything from compiling a GDS, merging masks, running simulations, DRC tests, integration tests. And once you have that, you can then generate a test report. And with that test report, you can check out certain things which are important for your chip. It can be, is your chip DRC clean? Is it conforming to specs? And you also generate a GDS output. Now it becomes interesting because now you can just run each iteration step by step, run it through the same automated system, and very quickly start to vary and see the test results and get GDS outputs. This is very interesting because for 3 different reasons. So one reason why this is super useful is that you always know where you are in your project because you have a reporting system that you can set up based on some specs which are important for your project. You can always know at any time where you are in your project and whether like you make a variation, oh, suddenly it's not DRC clean anymore. You can fix it quickly and so forth. The second is that you can always be ready for a tape out, and that's the continuous delivery part. So you're always ready to deliver when needed. And so definitely when you're in a tight schedule, having the confidence that at any moment in time you can make changes and quickly have a manufacturable chip can be very useful. And thirdly, this system allows you to validate or invalidate ideas very quickly. So making branches in a repository system is typically a very cheap operation, and you're encouraged to do that a lot. And so whenever you have an idea, you want to try out something quickly, you just make a branch, you do the changes, and your system will then again automatically generate these reports. So you quickly know whether an idea is worth pursuing or not. Of course, all these things don't come for free. So I'm plotting here the gain in terms of improving time to market versus the effort. So one of the things that we always advise our customers when they work with code is to use a version control system. It's fairly obvious to set up, and it already helps a lot in improving the quality of your code, fostering team collaboration and scaling your team. Second thing you can do is work on the automation in terms of making things repeatable, reducing the context switching. Like I mentioned, if 1 year from now you have to make a small change, if everything is automated to a large extent, this becomes easier. And also it internalizes the knowledge. So you can actually build recipes, so to speak, of all the designs that you make, and then it's easy from the recipe to see all the things that happened. And thirdly, so it takes the most effort, but also gives you a big gain, is this continuous integration and continuous delivery system, which I've been talking about, which is something you could install on premise with the right knowledge. And this helps you to validate and invalidate ideas more quickly, get your vector predictions, and always be ready for tape out. So to come back to my previous question, can we reuse techniques from software development and PIC design? Well, the answer is clearly a yes. And we see actually a lot of our customers adopting this approach and having a nice success with it. Okay, so thank you for listening. Also, just a small announcement. So IPKISS 3.4 will be released coming this week. So if you want to find out more, you can subscribe on our learning platform, which is academy.lucedaphotonics.com, or follow us on LinkedIn and Twitter. That's for the commercial part. Thank you.
Thank you very much, Martin, for that very nice talk. Just looking to see if there are any questions in the chat. I don't think I've got any. I'll ask one. You mentioned about dealing with uncertainty in the Foundry or other aspects. Is it through this kind of continuous integration monitoring process that you address this, or can you comment on this a bit further?
Yeah, so I mentioned two things. One is the uncertainty because of the manufacturing, and the other one is the uncertainty in terms of project planning. So if you think, I think the project planning is the most important part when you think of continuous integration and delivery, in the sense that because you get a test report, it's rather easy to follow up where you are. And so you can mitigate risks. So if you know that you're making changes in your design and suddenly all the tests to go red, then you know you did something wrong. And so in terms of dealing with risks, in terms of planning, this helps a lot. Indeed, in terms of variability, this then more relates to the specs. And so if you set up some tests, let's go back here. So imagine that, of course, depends on the user. So sorry. So here, if you think of a test report, it's of course up to the user, depending on the project you're working in, to set up a series of tests which will help you get to target or get your specifications. It can be the insertion loss has to be smaller than a certain number and so forth, and you can add them as specifications. And also, if you then run Monte Carlo simulations, you can do some kind of analysis on that and have that as part of your test suite. And again, this can help you, again, to cope to some extent with this variability. So if you make a change in your design and suddenly you see some of the specs start failing, it could be because of that variability.
Would the running of the Monte Carlo simulations impose a great requirement on computation or time?
Exactly. Yes, indeed. Yeah. Okay. So indeed, it's a trade-off that you have to make. Either you can always, and that's also what we do at Luceda, we have short testing, which can be done rather quickly, and then we have more high-level integration testing, where when everything is put together, only then we do, let's say, the more intensive testing.
Okay. Yes, that makes sense. Great. Thank you very much, Martin, for this very nice talk. I don't see any questions in the chat. Emma can correct me if there are. So in that sense, we're nicely to time. So I'd like to thank you again.